So I may sit down from time to time, but we'll see how this goes. So, well, I'm Howard Haber from UC Santa Cruz. I was asked to give lectures on supersymmetry, and well, there have been so many lectures on supersymmetry in TOSI over the years, it's hard to be original. So, in fact, I think I've given 2 of them at some point. Let me apologize immediately because there will be some fraction of you who will say, "Oh, I've seen this all before." But this is a school, and people coming from different backgrounds. So I'm going to give these lectures to be on the elementary side, but maybe there'll be a few things that you haven't seen before or haven't seen presented in quite the same way. So, I don't know if you can actually read this, but these will be posted, right, at some point. And I had to go to acronym.com to find out what SOL stood for, but all right.
Actually, what is SOL?
You can go to acronym.com too. Let's put it this way. The O and the L stand for out of luck, and I'll let you guess what the S stands for. All right. Super. There you go. Okay. So, I have 4 lectures and probably more than 4 lectures worth of topics. So I actually have 9 topics here, and I'm going to attempt to do 2 in each lecture, which doesn't quite work out. As Bernie Sanders said, I'm pretty good in arithmetic, but all right, never mind about that. So in any case, today I'm going to attempt, let's see, does this actually, yeah. So today, what I want to do mostly is to set up the formalism of 2-component spinors for a variety of reasons. One is that the formalism of supersymmetry is much easier when you deal with 2-component spinors. Second of all, it gives you a better appreciation for different types of fermions that we encounter, namely Majorana and Dirac Fermions. And so much of this lecture is going to be contained in that physics reports there, which you can easily find. In fact, if you go to my website, you can actually get the physics reports itself, or else you can find it on the archive. That physics reports has much more than you'll ever want to know about 2-component fermions and how to work with them. And in fact, a lot of what we do in that physics report is show you that you can even do all your Feynman diagram technology just from the 2-component language directly. But I won't quite do that in these lectures. So that will be most of today's lecture, and then just to get you warmed up for supersymmetry, I'll discuss some of the well-known motivations for supersymmetry, and probably that's where we'll finish today, and then we'll start with the details on Monday. Yes. So in these lectures, my personal metric is 1 minus 1 minus 1 minus 1. But if you insist on the other one, you can go on the archive, download the text file, and change 1 macro. And you will get the entire physics reports in the alternate metric, preferred by my co-author, Steve Martin. So, okay. So there are a whole bunch of other topics. We'll get to that when we come. So actually, I think I'm going to sit down if you don't mind. And occasionally get up and write a few things on the blackboard. So where we start in understanding fermions in quantum field theory is we go back to the basics, which is Lorenz transformations. And you know that a 4-vector transforms like so. And this lambda is a matrix, an element of SO3 comma 1. That's its defining equation. And as I said down here, the metric I'm using is 1 minus 1 minus 1 minus 1. Now you can look at infinitesimal Lorenz transformations and write out the generators, sometimes called J mu nu. I assume you've seen this at some point, and they have long commutation relations. But you can break up J mu nu into pieces, and there are 6 degrees of freedom here, and so the 6 degrees of freedom of the vector J and the vector K. And so basically your element of SO3 comma 1 is the exponentiation of this, and you can now discuss representations, n by n representations of the J and K matrices. Now, fields are defined to transform under the Lorentz group under n by n dimensional representations of the Lorentz group. And so it's a math problem to work out all the possible irreducible representations. And there's a clever technique of writing J plus and J minus as J plus or minus IK. And in most physics books, they just do this, and they don't tell you that this is completely illegal. You're not allowed to do this at all in mathematics, because this is a real Lie algebra. So what you're really doing, just in case, here's a little tidbit, is you're actually complexifying SO3 comma 1 into a complex SO4. Then you're allowed to take complex linear combinations of generators. You do get those commutation relations, and those are the commutation relations of the complex group SL2. And now you can just go back to the real version, which is, and the math still works. So this all works, but in case you're curious, that's what you're really doing. So, in any case, these are independent. Sorry? It's illegal to do it in SO3, in the real Lorentz algebra. This is just a trick to get you. All you want at the end of the day is these matrices, the J and K matrices. No, you do. You have spinor representations. Now, in the complexified as I said, this is in the complexified version SL2. But you recognize this. Everyone knows that this is the SU2 Lie algebra, and you know how to solve the representation theory for the SU2 Lie algebra. At the end of the day, this is a trick for getting matrices that are the irreducible representations of the real SO3 comma 1 Lie algebra. And this succeeds in doing that. I'm just filling in a little details about what you're really doing. So in any case, another way to say it is you shouldn't get the idea that SO3 comma 1 is the same as SU2 cross SU2. It is not. It is not. But nevertheless, this does get you the matrices, which is what we want. And so you know the representations of this algebra. Everyone learned that in their quantum mechanics course, and it's half-integer spin. And so J plus and J minus, you get 2 half integers. So J1 comma J2, and now you can start with the simplest one, 0 comma 0. That's a 1, and that's the trivial representation. And that's going to be where this is the just the unit matrix. Well, it's the number 1. So that's a scalar, but the next simplest possibility is either 1/2 0 or 0 1/2. And those are going to be our fermions, and they're two-dimensional. The next complicated one is 1/2 comma 1/2, which is four-dimensional, and that's actually a 4-vector. Okay, so now the nice thing is that not only do you know the dimension of the representation, you know the representation matrices, and those are the sigma matrices. And so the J pluses are the sigmas, and now you can work out what J and K is, and what you get is J is a sigma and K is an I sigma. And so at the end of the day, the 1/2 0 matrix is that, and the 0 1/2 is that one there.
So all the slides will be online.
Sorry?
So all the slides.
Yes, all the slides will be online. Now, if I have a matrix M, which is a representation of a Lie algebra, then M inverse adjoint is also a representation. It satisfies the same commutation relations, as does M star and M inverse transpose. So in fact, starting with one representation of the Lie algebra, you automatically get 4. Now, in many cases, those 4 don't give you anything new. 2 representations are said to be equivalent if they're related by similarity transform. Well, in this case, 2 of the 4 are independent, namely M and M inverse dagger. And the other 2 are not independent because they're related by similarity transform. When it's related by similarity transform, that's just saying you're writing the matrix on a different basis, so it's not anything new. So that means there are 2 inequivalent irreducible representations of dimension 2 of the Lorentz algebra. And so now when we go back to the field that transforms like that, we have 2 different types of fields, namely, say, that one, Xi with a lower alpha, and then this one, 0 1/2, that's that one there, which I'll denote by Xi with an upper alpha dot. So this is really heavy-handed notation, because I have both a dagger and a dot on the alpha. This notation is very old. It was from a time when, people didn't have tech, and they had to handwrite things, and they were worried that if you just put the dot there, it would smudge and you'd lose it, and then so they wanted to have a backup to make sure that you knew you were talking about 2 different representations. But okay. Now, if you go to most of the supersymmetry literature decided that instead of writing dagger here, they would put a bar, and so they would write C bar. Let me not get into the polemics of why my co-author Steve Martin insisted that we write daggers here instead of bars. But in any case, I will write daggers in these lectures. Now, this I sigma 2 here, which is the similarity transformation, is this little matrix here, and let me call it epsilon alpha beta, or epsilon alpha dot beta dot. And so that, in order to expose these 2 relations, it's useful to introduce, starting from that guy, which transforms under the matrix M, to introduce something with an upper index, which is not a new representation. It's just an equivalent way of writing the old representation. But this transforms like so if the upper guy and the lower guy are related by an epsilon like that. And it's just very convenient to introduce the upper indices and the lower indices. And basically, the upper indices and the lower indices are putting this equivalence into action. So I guess I should note that the what the dagger is exactly Hermitian conjugation. Now these are fields, so these are going to be anti-commuting fields. There are cases where you deal with commuting two-component spinners, and that's when you write spinor wave functions. A lot of that's in the physics reports. I'm not going to do that in these lectures, but you should know that both commuting and anti-commuting spinners are around. Okay, there's one more piece of notation here to introduce the sigma matrices. Sigma and sigma bar, defined like so. And why these are useful are as follows. First of all, let's look at this. So this M here is, again, the Lorenz transformation that acts on two-dimensional representations. And if you will remember that all 2x2 Hermitian matrices can be written as a linear combination of sigma matrices and the identity. And here's an example of a Hermitian 2x2 matrix. Therefore, it can be written as a linear combination. And I've written it like so. Same here. And the amazing thing, as you can show, is that the coefficients are just the Lorenz transformation that we started with, the 4x4 matrix that defines the SO3, 1 group. I'll indicate very briefly, well, the way you prove this is you have to find a clever way of writing M in terms of sigma matrices, and we'll do that in a couple of slides. And then it's a plug-in and a lot of messy algebra. So a little exercise if you want to test yourself in manipulations here. Okay, now if you stare at this, this also tells you what the index structure of the sigma and the sigma bar are. And I've written this equation out explicitly here. And here we will use a convention where we only sum dotted indices with themselves, undotted indices with themselves, and you only sum upper versus lower. Sort of like 4-vector summing upper versus lower. And once you adopt that convention, it's clear that the sigma matrix, and I see I've left out the mu here. It should be a mu, sorry about that. It's clear that the structure that I've shown here is the only way to do it. The fact that M has this index structure, that just came from setting up these transformation laws there. Again, and you can see I followed the rule of summing upper versus lower. Yeah. Yeah, there are lots of different conventions. So, go to here, go to Appendix A, I think. We have translations of how to go from one set of conventions to another. Yes, this is one of the minefields of this business and supersymmetry. There are lots of different conventions. The West Bagger, not only do they use a different sigma matrix convention, but they use the other metric. And I'm working in the metric I've told you, in the sigma convention I told you, and everything will be consistent in my lectures. And if you really want to see rules for translating, we discuss it a little bit there in the appendices. Okay. Now, there's a nice relationship between the sigmas and sigma bars and epsilon. I've written it out here. These come up a lot when you manipulate these things. Now, the real utility of having this object around is it allows you to construct 4 vectors from spinors. And here's the proof that this object here, and notice that I'm summing over alpha and beta dots, so the only free index is mu. So it would be nice if this thing were a 4-vector. And it is due to these relations here. And I've just written out the derivation. It's not too hard. And so what is the utility of all this notation? And so if you think about when you learned relativity notation and 4 vectors, there were up indices, there were low indices, you had all sorts of rules about what you were allowed to sum. But at the end of the day, the reason all that notation was useful is that if you had an object with some number of free indices, you knew immediately how it transforms under Lorenz transformation. And in particular, it allows you to construct scalars, Lorentz scalars, by summing all the indices. Now, what we're interested in is quantum field theory. And quantum field theory of fields are dictated by Lagrangians, which are Lorentz scalars. And so what all this technology is buying us is that once we learn the rules for how to deal with all the indices, etc., I could almost throw them all away. I can suppress all the indices, and I will know just by looking at an object how it transforms under the Lorentz transformation, and I will know whether I have a scalar or not, and so I will be able to construct Lagrangians out of the fields. And you don't have to prove over and over again that your proposed Lagrangian is Lorentz invariant, because the notation basically proves it for you. Yeah, so the dotted index is such that it transforms under this representation here. Okay, so as I just said, spinor indices can be suppressed, and in particular, the standard convention also used by Westenberger and almost everyone else in the supersymmetry literature is that you will, when you suppress indices, it means that you sum the undotted indices in this direction and the dotted indices in that direction. So now I have to think carefully. The undotted indices is north, west to southeast. Is that right? And luckily I'm a bridge player, so I'm just thinking of the hands, you know, and which one. Oh, never mind. All right. And this is, well, the other way. So in any case, you see how this goes. And it always works. So after a while, you don't even have to bother writing the indices. Now, here's one thing to keep in mind. For anti-commuting spinors, what this product here is that, and then I move that through that, which gets a minus sign. And now this is not in the correct direction to write it without the indices. So in order to do that, I have to use the epsilon symbols to raise this guy and lower this guy. And a little exercise for you to check that when you do that, you flip the sign. And so you get this funny result that for anti-commuting spinors, eta xi is equal to xi eta without a minus sign. It's hiding. So something to keep in mind. And one other thing we will need, because we want to construct Hermitian Lagrangians, is how to take the Hermitian conjugate of spinors. And when you do that, you reverse the order, and this capital sigma represents some product of sigma and sigma bar matrices. And it can't be any product, because it can only be a product where you could marry all the indices in the appropriate way. In fact, what you find is that this sigma can only contain products of sigma, sigma bar, sigma, sigma bar, etc. or vice versa. And so sigma r here means you reverse the order of the sigmas and sigma bars. Okay, so we now have almost all the ingredients. Here's one last piece of notation. I introduce sigma mu nu by definition and sigma bar mu nu by definition, like so. And what it turns out is that this is the object which, when you exponentiate, gives you the two-dimensional representation of the Lorentz group. And likewise, sigma bar gives M inverse dagger. So in fact, to prove that this result here is, you would use explicitly those formulas for M. Whoops. You would use these formulas explicitly, and then a whole bunch of relations between sigma mu's and sigma mu nu's, which I'll flash very quickly for you. Now, this is a very complicated matrix for a generic rotation and boost, and it's useful to see what it looks like for just a pure boost. So for a pure boost, I set theta ij equal to 0, and here are the matrices here. And explicitly, you can write them like so. For those of you who have used Peskin and Schroeder, you have seen the square root of p dot sigma, which Michael did not define properly in his book. So I've decided to define it properly for you. You can show that this is equal to this. The reason why I say not properly defined is because the square root of a matrix is not unique. And what you can show is that what you mean here by the square root of p dot sigma is this is a Hermitian matrix. So it's the unique Hermitian square root of the Hermitian matrix. And then it becomes unique, and that's what it is. And to prove this, you can just square both sides. Okay, lots of identities, which I will just flash, and there are even more identities in there. And these are some of the identities that will come up from time to time in our manipulations over the next few lectures. Just so that you know they're there. And the only other thing I point out to is you have to, when looking at a textbook, you always have to ask what their definition of epsilon mu nu alpha beta is. This is my definition. I would say 1/3 of the textbooks are defined like so. In 1/3 of the textbooks, this is defined as -1. And then the final 1/3 of the textbooks, they don't tell you how it's defined. And for all I know, it may be inconsistent. It just drives me nuts, but okay. So I insist always of letting you know what my conventions are. Now, here are some other relations, many of which we will use in the coming lectures. Now, I wrote these to allow for both commuting and anti-commuting spinners. In these lectures, all of our spinners will be anti-commuting, but if you go to the physics reports and you want to do Feynman diagrams with two-component notation, then you have to define two-component spinor wave functions, which are the analogs of the four-component U and V spinners, and those are commuting. So you have to also know how to deal with these products when they're commuting. And various Fiertz identities, which will come up from time to time. And Fiertz identities are basically the statement that an arbitrary Hermitian matrix is a linear combination of the identity in the sigma matrix. That's where you always start. And then you fiddle around, and you can get all sorts of interesting identities. Okay, so let's now get to some field theory. And so let's start with free field theory. And so if I want a free field theory of a 1/2 zero spinor, I have to find the kinetic energy term, which will involve a derivative. And I have to find a mass term, which will involve a product of, be quadratic. And I have to arrange it to be Lorentz invariant and Hermitian. And basically, there's only one choice. There it is. And this is the strength of the two-component technology. The indices, the dotted and undotted indices, are now hidden because I'm writing spinor products using my the southwest, northeast, whatever conventions. But you don't have to prove that this is Lorentz invariant. It is automatic now. Now, a very slight cheat. Well, this is Hermitian. By the way, you might ask me why didn't I allow M to be complex here, and then I would write M times this and M star times that. The answer is because I can always rephase that away by redefining the complex C. And so without loss of generality, I take M to be a non-negative number, real number. This guy is not Hermitian, but I can rewrite it like so, and this is Hermitian. And so, since all we care is Lagrangians up to a total divergence, I'm going to stick with this. Now, you'll notice I wrote this with sigma bar and not with sigma. I could have written it with sigma using one of these. You'll notice this result here relates a spinor product with sigma and a spinor product with sigma bar. So they're not independent. And it's conventional which one you choose. I've chosen the sigma bars to write all my derivatives. Now let's generalize this to a multiplet of two-component fermions. Here it is. And now here I do have a complex matrix. One other piece of notation that's useful is when you have flavor indices. When I raise a flavor index, that's equivalent to complex conjugation. So just keep that in mind. It's a convenience. You don't need to adopt that convention, but I will here. Now, if you want to interpret this as a field theory of physical particles, we're going to have to identify the mass eigenstates. So how do we do that? What we're going to do is we're going to take our interaction eigenstates, which had hats on them, and rewrite them in terms of mass eigenstates according to this unitary matrix omega. And if you plop that transformation back into here and require that you have diagonal mass terms, you get the following diagonalization problem, which is this. Oh, let me emphasize one very important thing. This M here is not only a complex matrix, it's symmetric, mainly because of the structure here. And that's important. So we have a diagonalization problem where M is an arbitrary complex symmetric matrix. And so this is not the diagonalization problem you learned in your linear algebra classes. This is a different type of diagonalization problem. It was solved actually in the early 20th century and rediscovered about 10 times afterwards, including by physicists who also rediscovered it and had no idea it was known before. If you go to a very nice textbook by Horn and Johnson, you will learn that one of the originators of this was a Japanese mathematician named Takagi. Although they later discovered he wasn't the first, he was the second, but never mind about that. And the diagonalization problem is to find an omega such that this is a diagonal matrix with non-negative real numbers, and those are going to be the masses. And well, one way of doing that is to note that you can rewrite this like so, and then this looks more like an ordinary diagonalization problem of MM dagger. And so you can diagonalize that by standard techniques, and that gives you M squared. Then you take the positive square roots to get this up here. And once you've done that, here is, in terms of the mass eigenstates, the Lagrangian is just a collection of free 1/2 zero fields. Okay, so here's one of the famous examples of this called the Seesaw Mechanism. Here's a little model of two Majorana fields called psi1 and psi2 with this 2x2 mass matrix. And so we want to do a Takagi diagonalization of this mass matrix. And the now, for some reason, instead of omega, I called it U. But here's the U that you need. The masses that you get are this. Notice that they are positive masses. And you even have a formula for theta. And then you can look at the very interesting limit where capital M is much larger than MD. Let me just emphasize that that's this guy here. Of course, this is the model for producing massive neutrinos, where this is like a Dirac mass, and this is a heavy right-handed neutrino. And so at the end of the day, you get this result here, where one mass is very small, md squared over capital M, where M is much larger than md, and the other one is of order the heavy mass M. And you get two Majorana fermions out of this. Okay, now, if you have a multiplet of fields, one should always check to see if there are global symmetries. And the simplest example of this is a model of two 1/2 zero fields called chi and eta with the following Lagrangian. This is not the most general mass term of that Lagrangian. But suppose I gave this to you, you would look at that and say, aha, there's a U1 global symmetry in which chi and eta transform oppositely. And so that suggests that there's a symmetry. Use Noether's theorem, et cetera, you get a charge. And so this is a theory of two oppositely charged fermions. And now, this is not a diagonal mass matrix, so you can do a Takagi diagonalization and get the masses out. You will find that the two masses are exactly degenerate, and in fact equal to M. But when you go to the mass eigenstate basis, you will find those mass eigenstates are not eigenstates of charge anymore. Now, this is completely analogous to a free field theory of a complex scalar with a mass term m squared, absolute value phi squared. And you all know that you can write phi equals little phi 1 plus I phi 2 over root 2 and get a diagonal mass matrix. But phi 1 and phi 2 are not eigenstates of the charge. It's exactly the same. So what we will do is we will not do a Takagi diagonalization of this. We will say this is your basic model for a charged fermion. And in fact, chi and eta dagger, since eta and chi transform oppositely, chi and eta dagger transform the same way, represent a single charge. And this, of course, is your four-component Dirac Fermion. We can even consider a collection of Dirac Fermions. And when we consider the Lagrangian here, now my most general mass term involves a complex mass matrix which is not symmetric. It's just a complex mass matrix. And how do we identify the physical mass eigenstates? Well, chi and eta both get related to their mass eigenstates by two different unitary matrices, L and R. And then when I plug that back in there and require diagonal masses, diagonal in the sense of Dirac, I get the following diagonalization problem. So here's another diagonalization problem, which is not the diagonalization problem you learned in your linear algebra classes. This one actually is called the singular value decomposition. It has lots of other interesting applications. But here, the object is to find the unitary L and the unitary R such that this is a diagonal matrix with non-negative masses. And again, when you do that, it's easy to figure out what the M1, what these masses are by solving that ordinary diagonalization problem. and then plugging the mass eigenstates back into here, you get now your collection of Dirac Fermions of mass mi. Sorry? Can I go back?
It's a typo.
Yeah, it's a typo in there. Yeah.
What did I have?
Global symmetry.
Oh, yes. See, thank you. All right, so that's two typos to fix before we post. Okay, now, so far we've done free field theory. Now let's put in the interactions. So I'm going to just run through this very quickly. Here are some Yukawa interactions of scalars and fermions. You first write it in terms of the interaction eigenstates, then you do the mass diagonalization. Now here I'm sort of putting, I can break up all my fermions into a set of Majorana fermions and a set of Dirac fermions if the global symmetries permit, do the diagonalization problem, and just rewrite everything in terms of mass eigenstates. And actually do the same for the scalars as well. That will also have a mass matrix. That diagonalization problem is the one you're familiar with, the similarity transformation. For gauge theories, it's similar. You start with this interaction here. The T is the representation matrix for the gauge group. Well, how the fermions transform under the gauge group. And you can consider both unbroken theories and broken theories. For broken theories, you have to work out the mass matrices of the gauge bosons and then redefine the generators. That's, hopefully you've learned that all in your classes. And so you end up, in terms of mass eigenstates, getting an interaction like that, where this U was this diagonalization matrix here that combined everything we need to get the fermions right. Now, this is sort of generic, but I can specialize to the case of Dirac Fermions. And for the case of Dirac Fermions, it's just interesting to note that the chi lower I and eta upper I transform as conjugate representations of the gauge group. And so for the conjugate representation, the relevant generator is minus TA star. And so in the end, for the Dirac case, you can write it like this, and you get this extra minus sign. Okay. Now, if you're a believer in this physics reports, you wouldn't have to go to this next step. But since most of you were trained in four-component notation, I'm going to give you now the translation and discuss a little bit about how to deal with Majorana particles in four-component notation. So, I put together the gamma matrices out of the sigmas, like shown here. This is called the chiral representation of the gamma matrix algebra. There's also a sigma mu nu, which is usually denoted by little sigma in textbooks, but I've called it capital sigma here so that we don't get confused between that guy and that guy there. And then the four-component Dirac spinner. Remember, a Dirac guy was a combination of a chi and an eta dagger, and so let's combine them. It's natural to combine them into a four-component spinner. Now, in order to construct Lorentz invariants in four components, you have to define a psi bar, which is related to psi dagger by, in textbooks, it's called gamma 0. But when you're doing this translation, it's actually not useful to call it gamma 0. So I'm going to call it A. And explicitly, it's related like so. And now you can check that psi bar psi is a proper Lorentz scalar. And I also introduced the charge conjugation matrix here. And A and C have these properties here. And in fact, there are additional properties that are conventional to assign to A and C, which I've written down here. And so when you use those properties, you get a unique form for A and C. And you'll notice that A numerically is the same as the gamma 0, but it's not the same, because gamma 0 involves sigma matrices, and A involves something, well, with different two-component index structure. So that's why I will not use gamma 0 explicitly. But of course, when you do actual calculations, you can use gamma 0. But at the end of the day, all it really depends on is that relation there. And now you can start to write translations of various things, and 4-component things on the left, 2-component things on the right. So there are a bunch of useful results, and here's a table relating a whole bunch of bilinear covariants in terms of their 2-component quantities. Now, by the way, remember, when I write something with a sigma bar, I always have the option of flipping it and writing it in terms of a sigma. So, again, just keep that in mind. You have that choice about what you want to do. Now, what's a Majorana fermion? A Majorana fermion in 4-component notation is a self-conjugate 4-component fermion. And so it satisfies this relation here. And that's kind of nasty. It's a nasty relation. So this is why Majorana fermions in 4-component in Feynman diagrams is such a headache. And when you think about it, it really shouldn't be a headache. After all, when you do scalar field theory, you start out with a real scalar, and that's a neutral guy, and then you learn about complex scalars, which are charged. And the relationship, if I have a capital phi and I want to say it's neutral, I say phi star equals phi. And it's very simple. And you don't have to suffer to deal with neutral particles. And in the 4-component notation, because of this extra complexity, it gives you extra headaches. And so I'll show you within the 4-component context how to deal with that. But it's one reason why it's very nice to be able to, at least in principle, know how to work with 2-component fermions from beginning to end, even in evaluating Feynman diagrams. But in any case, here are some interesting relations of what the self-conjugate condition on a Majorana fermion does. It relates bilinear covariance. If I have 2 of them, 2 Majoranas, it gives you these relationships like that. And in fact, if you look at these, if number 1 and number 2 are the same, you find that 3 of these are exactly 0. This first one being 0 is basically saying it's neutral. You can't write a current. The fact that these are 0 is telling you that a Majorana fermion doesn't have a magnetic or electric dipole moment, which is kind of an interesting aside. Okay, so how do we deal with Majorana fermions if you insist on using 4-component technology that you all learned in your quantum field theory classes for computing Feynman diagrams? How shall we deal with Majorana fermions? And it turns out that it's very easy to deal with Majorana fermions if you make a very small change in the way you do things. And in some sense, the reason why this is not in any of the textbooks is because the Feynman diagram technology came out of QED, and QED is a vector-like theory with charged fermions and no neutral fermions. And so, in some sense, things were simplified from day one, and you didn't ever learn about what the original Feynman rule should have been before the simplification of vector-like theories came around. Now, in fact, if I take electroweak theory, which is not a vector-like theory, it's a chiral theory, even if I don't have Majorana fermions, although since we have massive neutrinos, I'm willing to bet that there are even Majorana fermions in electroweak theory. But even if you discard that, the fact that you have to always break things up into left and right-handed things in electroweak theory, you would not even notice you were doing this if you were working on the two-component level, because it's already in that form. And it's so to write the standard model Lagrangian completely in two-component notation is in fact much more natural than trying to force yourself into defining left-handed fields, right-handed fields, and the left-handed fields transform differently from the right-handed fields. And I remember when I was a student, I was completely baffled by that. I mean, we started out with a Dirac Fermion, and then suddenly we were breaking it up and assigning different quantum numbers to it. This is completely natural in the case of two-component fermions. You wouldn't even think about not doing that. You have a collection of 1/2 zero fields. That's all you start off with. And each one you have to assign a quantum number to it. It's the most natural thing to do. Okay, so Feynman rules. First, the propagator. Luckily, it doesn't matter whether you have Dirac, Majorana, partly because the propagator is the same whether you're using the field or the charge conjugate fields. So now let's consider how we would write Feynman rules for a theory with a set of neutral Majorana and charged Dirac fermions interacting with scalars or vectors. So we start out with a Lagrangian that looks like this down here. And I've written it in two-component notation. I've put labels I and J, those flavor indices, because I have lots of different fermions around. So what I'm going to do is I'm going to write Feynman rules for this. And the way I'm going to do it is I'm going to use those translation tables, namely all that stuff there, and just rewrite this in terms of four-component notation. And once I have that, I can read off Feynman rules in the standard way. And when you do that, there you get a bunch of Feynman rules. Now, when you do this, because you're, let's just go back here, you will see that lots of these, when you see a spinor product and you rewrite it in four-component notation, sometimes it will involve the charge conjugate field as well. So I get vertices with charge conjugate fields, but again, I just read them off in the standard way. And so, for instance, in this case, I can either have that or that. It has the same Feynman rule. And similarly, this one or this one will have the same Feynman rule. Now, in Feynman diagrams, fermions have arrows. What do those arrows mean? Well, when you learned about this in your quantum field theory, you were taught that arrows follow the flow of conserved charge. So what do we do about a Majorana fermion, which is self-conjugate? Well, in that case, the arrow is going to just reflect the structure of how the field appears in the interaction Lagrangian. So in the usual way that psi bar is represented by an arrow pointing out of the vertex and a psi pointing in. And moreover, the arrow directions determine the placement of the U and V spinors if they're external particles. And now here is the key point. When you write a set of diagrams, if you have a Dirac fermion, you can either represent it by the field psi or by the conjugated field psi. You don't do both. You have a choice. And in fact, if you write it in one way, you can relate it to it written in another way. And so, for instance, here I've shown you how the bilinear covariants are related. They're related by either plus or minus one factor. And so we're going to use this in 1 minute. Let me write down one other set of. So here we had a set of neutral scalars or neutral gauge bosons interacting with fermions. I can also have charge scalars and charge bosons. And so that Lagrangian is going to look like this. And again, the idea is to use my translation table, rewrite it in 4 components, and then read off the Feynman rules. There are the Feynman rules that you get for that. And again, you have choices. So either that or that, depending on whether you represent this fermion with a psi or a psi conjugate. You don't do both. You pick one. And then finally, for outgoing, so this is, as I say here, one is free to choose either psi or psi c line to represent a Dirac fermion. That's going to be the key to making our life very pleasant when we do Feynman diagrams. Then finally, there are the external wave functions. I've written them here. And the only difference from what's in Peskin and Schroeder is I'm telling you how it works with psi c as well. So now we come down to the invariant amplitudes. And so here's the deal. First, you have to figure out how many distinct graphs there are. So you write down your graphs, but you don't put any arrows on them. You just figure out, without the arrows, how many graphs there are. Then you put the arrows down, and the choice of whether you use psi or psi c is governed by the following desire, which is to have arrows run continuously through your diagram. Never have a clashing arrow. And so, in our example 1, where we have the scattering of 2 Dirac fermions through a Majorana-fermion exchange, there are 2 graphs. There they are. And then you'll notice that I have represented one of the incoming fermions with a psi and the other incoming fermion with a psi c. They're the same fermions. This is not fermion-anti-fermion scattering. This is fermion-fermion scattering. And so when I represent the fermion at the bottom, you'll notice the arrow is pointing out. A psi c pointing out is basically the same as a psi pointing in. So that's the choice I make. And when I make that choice, then the arrow on the Majorana fermion is unique in order to have a continuous arrow there. Now, if you tried to do this without what I just told you, you would then be scratching your head because you'd have 2 arrows coming in, you'd have the Majorana fermion coming down, and you'd say, what do I do with this? And then I admit that when I first wrote my physics reports with Gordy Kane on supersymmetry back in 1985, we ended up defining all sorts of propagator lines with arrows clashing and vertices with arrows clashing, and we had charge conjugation matrices all over the place. And you could do it that way, and it's horrible. It was only later I realized that that was all unnecessary. All I had to do was be a little clever here and represent a fermion sometimes as psi c. And then I can always guarantee the arrows being continuous, and then I can use my Feynman rules in the standard way, and everything goes through. And so there I've written the matrix element from those 2 diagrams over there. And you might want to check that since I have 2 identical fermions coming in, that this amplitude changes sign. if I interchange the order of the two fermions. So there's your little homework assignment, is to check that in fact it is, that this amplitude is antisymmetric. And by the way, in doing this check, if you make use of this nice relation among U and V spinors, you will be able to double check that very quickly. So example 2, now I'm going to do fermion anti-fermion scattering into a pair of Majorana fermions. And now I actually have two choices. There are two ways of laying down the arrows continuously by making different choices for which one is psi and which one is psi c. So you'll notice in diagram set 2, I used the psi in both cases, but you'll notice the arrow on the bottom psi is pointing backwards. That tells you that it's really particle-antiparticle scattering. Okay, now, which set should I use? The answer is it doesn't matter. You don't do both. You make one choice. And you can show pretty easily that that the sum diagram set 1 and diagram set 2 at most differ by an overall sign. But the overall sign of an invariant amplitude involving fermions is not well defined. It's conventional. By the way, also, a nice thing about these this way of doing things is that the relative sign between two diagrams is automatic. Basically, you look at the order of your spinors. You write out your spinors, the U and V spinors, and now you look at the ordering. And so, for instance, in diagram set 1, you always go backwards, follow the arrows backwards, and lay down your spinors. So you would do 3, 1, 4, 2 here. Here you would do 4, 1, 3, 2. And those two numbers are odd permutations of each other. And that tells you there's a relative sign between these two diagrams. So there's one step left, which is when you add the two diagrams and you sum and square, you will have interference terms. And when you have interference terms, if you just have standard QED, you always get, the projection operators for the U and V spinors in the standard way. But when you do it here, you are in danger of running into weird projection operators like this, which involve charge conjugation matrices. However, you can even avoid this happening because you have some nice relations between U and V spinors. And so if before you add up and square, you choose an appropriate, if you have this, you may want to replace it by that. And remember, we had this. If you had this, you might want to replace it by that. If you make judicious choices, you will never end up with anything that looks like that. And so in this way, you can treat Majorana fermions in 4-component Feynman diagrams perfectly well without ever seeing a charge conjugation matrix. Okay, so I'm about 5 minutes behind, but I think we started 5 minutes late. So that was the end of section 1, but section 2 is a short section, which is the motivation for TV scale supersymmetry. So I've basically now set up all the formalism we will need over the next 3 lectures, and you can now do calculations. And if you don't want to do Feynman diagrams using 2-component technology, you can use the 4-component Feynman rules and do scattering of neutralinos in all sorts of ways, and perfectly well treat the Majorana fermions in a natural way. Sorry? Yeah, I thought about that as I was preparing these lectures. I say, is this even worth it? Because, the modern student, when it comes to, at some point you should do one calculation yourself just to check. you know, do all those programs, do all these things correctly and get all the signs right, you might want to check from time to time that they're doing it right. All right. So, motivation for TV scale supersymmetry. You know very well that the reason why I'm giving supersymmetry lectures is that there is still hope, unlike the cartoonist on the first page, that we might discover supersymmetric particles at the LHC. And so why has this been this long-standing program to search for supersymmetry at the LHC? I mean, the standard model is incredibly successful, but we know there are missing pieces. Neutrinos are not massless. The Seesaw Mechanism I mentioned was one way generating neutrino masses, introduces a new high energy scale. We know dark matter is not accounted for. Baryon asymmetry of the universe is not accounted for. Inflation is not accounted for. Gravity is omitted. It is clear that the standard model, as nice a theory as it is, it's an effective field theory, and a new high energy scales must exist where more fundamental physics resides. And indeed, you know, gravity is most likely governed, well, quantum gravity is most likely governed by the Planck scale, which is a very large scale, 10 to the 19th GeV. For those of you who don't remember where that number comes from, you just take the gravitational potential energy, evaluate it at the Compton wavelength, and you set it equal to the rest mass squared. Because that's the condition that's telling you that you have the potential for pair production due to the energy in the gravitational field. Once that happens, you know that you need quantum physics to adequately describe that. So in general, I'll use lambda to denote the scale at which new physics enters. And so the predictions made by the standard model depend on parameters in the standard model that you can compute within the standard model. And they are sensitive to ultraviolet physics in some unknown way. We don't know the precise theory of fundamental physics at arbitrarily high energies. So we can't compute the mass of the electron or the Yukawa couplings or what have you. But you can determine the sensitivity of these parameters to the ultraviolet scale. And it's been known for an incredibly long time, in fact, since the 1930s, that fermion masses are logarithmically sensitive to ultraviolet physics, whereas boson masses are quadratically sensitive to ultraviolet physics. And I'll say more about that in a minute. Now, you'll often hear the statement that the Higgs mass is how shall I put it? Well, quadratically sensitive to new physics, et cetera, et cetera. But I remind you that that's actually an inaccurate way of putting it, because I've written up there the Higgs mass is being proportional to Higgs self-coupling and the vacuum expectation value squared, the W mass proportional to the gauge coupling. The ratio of the Higgs mass and the W mass is of order 1. And that's perfectly fine. I mean, 125 GeV Higgs, that's spot on. So where is the quadratic sensitivity coming? It's coming really through the vacuum expectation value. And so one way to say it is if you go to the Higgs potential, this parameter mu, which is related to the vacuum expectation value, that's the thing that's quadratically sensitive to ultraviolet physics. And one way of saying this is if I have new physics and I do a one-loop calculation, if I cut it off at the scale lambda, then I want that contribution to be roughly of order the tree-level contribution. Otherwise, I have to fine-tune two terms together which have completely different origins. The tree level parameter would be something set by some large scale. the one-loop calculation is a calculation you do in the Lorentz effective theory. And when you set those two quantities equal, you find that that would make sense only if lambda is roughly 4 pi v over g. Now, there are lots of numbers missing from here. If I take 4 pi v over g as given by measurements, I would get something like 5 TeV. So I'm not distinguishing 1 TeV and 5 TeV here. And so you would say that a natural theory of electroweak symmetry breaking requires new physics at the TeV scale. So where did this principle of naturalness come from? The amazing thing, it was first written down by Weisskopf in 1939. And if you go to this paper, which I've displayed up there, in the abstract, he has the following statement, and I think this is the first time the statement ever appeared in the literature. The self-energy of charged particles obeying Bose statistics is found to be quadratically divergent. And what he concludes from that is that in theories of elementary bosons, new phenomena must enter at an energy scale of over m over e, where e, in his case, was the coupling constant, the relevant coupling constant. And this is basically what I just said over here. So this is the origin of naturalness. Of course, these days what we say is we ask the question of how do we understand the magnitude of the electroweak symmetry breaking scale. And our alternatives are, if the Higgs is an elementary fermion, then maybe naturalness is restored by some new symmetry principle, and that's going to be supersymmetry, which will relate the bosons to the fermions, and the fermions are only logarithmically sensitive to ultraviolet physics. But there are alternatives. The Higgs might be an approximate Goldstone boson. It might be a composite scalar. Or maybe naturalness doesn't even apply. And the Higgs boson is very unlikely. Shudder when you see the word landscape. But in any case, there are many of my friends who insist that this is the more likely explanation these days, since we still haven't discovered any new TeV scale physics. I think this is a little bit too early to be throwing up our hands. But, you know, a few years from now, 10 years from now, you know, depends on what LHC discovers. Of course, it might announce the existence of a 750 GeV scalar 2 months from now, and then we'll all be doing something else. But okay. So how do we avoid quadratic sensitivity to lambda with elementary scalars? And so there's a very nice lesson from history, which starts off by observing that the electron self-energy in classical electrodynamics is linear divergent, basically from Coulomb's law. And in quantum field theory, it's even worse. If you look at effects of fluctuations of electromagnetic fields in single electron theory, you actually get a quadratic divergence. And that's a disaster, because as argued by Weisskopf, it would require new physics at the order of the mass of the electron divided by E, which is a mass scale which we've already surpassed. Now, here's the amazing thing. That linear and quadratic divergence cancel exactly if you make a bold hypothesis that you don't only have electrons in the universe, but you have positrons with a mass equal to the electron but opposite in charge. So in fact, all we need to do is to take our single electron theory and double the number of particles, and say for each particle, namely the electron, it has a partner particle, which is related by symmetry. And due to that symmetry, magically, the quadratic divergence and the linear divergence disappear. Now, this cancellation was first demonstrated by Weisskopf again 5 years before that previous paper. So that previous paper I showed you was a follow-up to this. He discovered this in 1934. Well, he sort of discovered this in 1934. Actually, that was the paper in 1934. And if you read, I don't know if you can read the abstract, the last sentence says, as expected, the self-energy also diverges in this theory, specifically to the same extent as in ordinary single electron theory, namely quadratically divergent. He got it wrong. Then he got an email, except it wasn't an email. It was probably a physical letter from Furry saying, Professor Weisskopf, I found an error in your algebra, and when you correct it, the quadratic and linear divergence cancels, and so an erratum appeared which says the divergence is only logarithmic. Now, I want you to be really amazed by this, because can you imagine this happening today? The paper appears on the archive with the algebraic error, and some guy works through it and discovers that there was an algebraic error. What do you think that person will do? So it's a different time we live in today compared to back then. Well, except 5 years later, he interesting. Okay, well, here was the cancellation, the remarkable cancellation, in sort of an old-fashioned time-ordered perturbation theory picture. And so my last slide, and this is where we finish today, TeV supersymmetry to the rescue. So if we were successful in canceling the unnaturalness, solving the unnaturalness problem of single electron theory by doubling the spectrum, adding a new symmetry, and therefore canceling the quadratic divergence, who says we can't do it again? And so let's invent a new symmetry, and for every boson we have a partner fermion with the exact same mass and vice versa. And then we start to do our self-energy calculations, and lo and behold, if we set it up correctly with the symmetry that we need, which will be supersymmetry, the quadratic divergence will exactly cancel, and we are back to logarithmic divergence as in 1934 with Furry's correction to Weisskopf. Okay, well, that's great, except there aren't any supersymmetric particles with the mass of known standard model particles. That we know today. There's no selectron with the mass of the electron. So the analogy falls a little bit flat on its face. However, we can try to repair that by saying, well, okay, supersymmetry is not an exact symmetry, but it's an approximate symmetry. And then the question is, how approximate a symmetry do we need in order to solve the naturalness problem? And the answer is we need it to be approximate symmetry up to about the TeV scale. And so that would suggest that if supersymmetry is responsible for understanding a natural explanation for electroweak symmetry breaking, then the supersymmetry breaking scale better not be much larger than about 1 TeV. Now, this is where you come to questions about degree. If supersymmetry comes out to be 5 TeV, will we all throw up our hands and say, this wasn't the solution? Well, we'll have to see. There are those who argued that supersymmetry should have been not 1 TeV, but 100 GeV, and therefore supersymmetry is not the solution. On the other hand, if one were to discover supersymmetric particles in the 1 to TeV mass range, you would have a way of understanding at least how the TeV scale is stable compared to the Planck scale or the grand unification scale. And that's a pretty large hierarchy right there. That's, let's see, 10 to the 19, 16 orders of magnitude. So if we have gotten some fundamental understanding of how 16 ordered, hierarchy of 16 orders of magnitude is stable, then maybe I won't sweat too much about a factor of 10. This factor of 10 is called the little hierarchy problem, and it's worth thinking about. But people spend a lot of time talking about measures of naturalness. And the problems I have with that is that we don't have really enough information to really know what the right measure of naturalness is. You know, you can make statements that are independent of what the ultraviolet theory is. But at the end of the day, the ultraviolet theory might lead to some interesting relations between parameters and might buy you a factor of 10 here and there. And so I think the jury is still out. And I'm just sort of waffling here to give you an excuse to come back to my lecture on Monday, where we actually start to look at supersymmetry seriously. Still to be understood, by the way, is the fundamental origin of supersymmetry breaking, which is a difficult problem, and I will finesse that problem in the lectures. I think you need a separate series of lectures to really discuss supersymmetry breaking, and at the moment we don't have the compelling theory of supersymmetry breaking. There are lots of different candidates out there. So I'll stop right here. Thanks.